Mars has given us a lot of good things over history of time. Mars has given us, first of all, the ability to be fascinated about a red planet that we actually can see with our naked eyes on some nights. It's a place that has driven all kinds of science fiction, fantasy, invasion of the planet. It was very important, of course, for ancient cultures and its position within mythology and other aspects of culture. So Mars is a critical component of the human experience. But something about Mars that we don't think about is how fundamental it's been for driving forward our ability to understand a new version of evolutionary biology in the context of a changing Earth. And that fundamental capability of Mars to change the way we think was driven by the following. Every year, a huge amount of rock material, and I'm measuring this in terms of tons, so tons and tons of rock material on a yearly basis has been dislodged from Mars because of meteor impacts, blasted into the solar system, thrown into the pathway in which the Earth is spinning around the sun, and every time the Earth goes through a dust and rock field that was generated by debris being blasted off of Mars from meteor impacts, every time the Earth goes through these clouds of dust and rock, that dust and rock is collected into the atmosphere and falls to the Earth. Now we know some of this from the space shuttle heat shields. The heat shields have been analyzed, and every time the space shuttle goes in and out, it would collect rock and dust material. And by analyzing the chemical composition of the rock material that is collected from the heat shields, Mars has a very distinct chemical signature from that of Earth. So we have a fingerprint. If we have a rock that came from Mars, we can tell that distinctly from a rock that came from Earth. Now what's really exciting about this is that not only are the space shuttles great collectors of Martian rock and dust, but on a natural process, rock and dust hits the Earth, it settles through the atmosphere, it hits the planet's surface, and the rock and dust that hits the surface on the ice fields, places like the Antarctic, where we have 1.8 kilometers of ice that's just sitting there on the poles, that ice field becomes the perfect trap for collecting dust and rock that falls in from space and hits the planet. Now, at any one time, that dust and rock will hit the surface of the ice, and then as more snow falls and more ice is formed, then that dust and rock gets collected and trapped within the ice. Now, ice sheets like the Antarctic are really dynamic places, and by that I mean that in some places they're forming and in some places they're melting. And on a yearly basis, parts of the ice sheet are known to actually melt, or what we call ablate, go from one phase that's actually a solid ice phase directly into a gas phase without becoming a fluid or water. So parts of the ice sheet are changing and going from solid ice into water vapor. And in those places, the ice sheet deflates. It actually decreases in mass, and anything that's trapped within the ice becomes sitting on the top of the ice as the ice slowly fades away and becomes more compressed and dense underneath of it. So you have the ice sheet then disappearing, in its rock and ash and particle load that is collected over the millennia is now sitting free on the surface because of that deflation of the ice. Well, NASA's known this for a long time. So every year NASA scientists go up and they take snowmobiles and they collect all kinds of meteors that have hit the Earth. Meteors are actively flying through space, and Meteorite is one of these meteors that has hit the planet and stopped moving. So they go around the ice sheets and collect meteorites off the surface of the Antarctic. And those meteorites are put into massive collections that are held at the Smithsonian or at NASA or at other places, and they're held for future analysis by scientists, because every year enough are collected to overwhelm the scientific community. There's a lot of material that needs to be looked at. Well, we got really lucky because of a confluence of circumstance that came together. One of those was that NASA had an ongoing research program in terms of looking at meteorites that had hit the Earth, and then looking for fossil evidence of what that life is. Another one is that some of the right meteorites were actually collected. And so there's a famous one that ended up being the rock sample, the meteorite that changed the face of science and our ability to understand evolutionary biology. And that's called the famous Martian meteorite. And the Martian meteorite was given a name. It's ALH 84001. ALH 84001. If you Google that number, you will be amazed at what you find. That was the number given to that particular meteorite that was collected in the year 1984, hence the number 84. And it was collected from a part of the Antarctic ice sheet called the Allen Hills, ALH. And the Allen Hills region of the ice sheet at that time, in 1984, there was a beautiful potato-sized rock that was laying there, a meteorite. And it was collected, given that catalog number, and then put into a collection. Well, a few years later, a NASA scientists, especially out at NASA Ames Research Center out in California, they started looking for fossil evidence of microbes within rock. And it's not easy to do. Microbes, their average diameter is 1 micron. These are small creatures, and they have many aspects of them that are hard to distinguish from non-biological entities. So telling the difference between a biological fossil and a non-biological fossil that's on the scale of 1 micron is a major challenge. So NASA scientists were looking carefully at these meteorites that were collected, and the ALH 84001 turned out to be a piece of orthopyroxene. Orthopyroxene is a form of igneous rock. Igneous rocks you know about more commonly are things like granite. People like to put them on their countertops. Well, orthopyroxene is another form of igneous rock. It's crystals that cool and grow together that come out of a molten mass of rock. And this particular meteorite, it was formed originally as an igneous rock on the planet Mars. And then while it was still on Mars, it formed, became a solid rock, and then it was fractured. And we don't know exactly the process that fractured it, but some kind of strong geological process would have had to have fractured the rock while it was still a component of the crust of Mars. Now, after the rock was fractured, waters started moving through the rock. And as waters move through rock like that, oftentimes they'll precipitate minerals. So you can have elements that are dissolved in water, and if you flow the water over something, change some of the physical chemical conditions, you can actually have those elements go from being ions in a water to something that's solid. Now you do this in reverse all the time. If you want to put sugar into your coffee, right, you'll put sugar in and then you'll stir it, and it goes from a solid sugar clump into disappearing, which means all the ions that make up the sugar go into the water. So as these waters on Mars flowed through these fractures in the piece of orthopyroxene, they precipitated a very important mineral, the mineral calcite, calcium carbonate, CaCO3. And calcium carbonate is really important to us because calcium carbonate is often associated, not always, but is often associated with biological activity. If something's living there and they do some kind of a process to keep themselves alive, then one of the things that happens as a result is the water will allow the ions to go from being dissolved to being a solid mineral. So these solid rock minerals actually grow out of the water as the water flowed through these cracks, and they were trapped in the calcium carbonate and filled up this fracture in this igneous rock from Mars. Now we have good and actually very excellent analogs for this, comparative environments on Earth where we see this happening all the time. A very famous one is Mammoth Hot Springs in Yellowstone National Park, where the waters come up to the surface of the Earth after being heated by a supervolcano. They are full of ions that once the waters cool and allow some of the gas to escape from those waters, they precipitate calcium carbonate at incredible rates, very, very, very fast. So we know from Earth environments that this can happen. Well, all this process took place on Mars, but then one thing happened a very long time period after that rock was formed, is that a meteor hit Mars, created a crater, and then blasted rock material into space. Then that chunk of orthopyroxene with a fracture filled with calcium carbonate with potential microbial fossils in it, it traveled through the solar system. It left the orbit of Mars, went into orbit around the sun, and as the Earth came around, it entered the Earth's atmosphere and then plunged to Earth in the Antarctic. Then the funding agencies, especially in the United States, but also in other countries, began making opportunities for scientists to look carefully at what is a fossil that is microbial in origin versus what is a fossil that is not microbial in origin. And therefore the famous Martian meteorite really opened the door for scientific discovery to lay the boilerplate then for us to understand the genesis of life not only on planet Earth but also potentially on Mars.